this module. In the first video, we studied SVM and kernel methods and their quantum versions. Now we will continue with some other popular machine learning methods and their quantum versions. The first thing we studied is what is called dimensionality reduction or feature extraction in machine learning. In machine learning, often the observations xi, which belong to some vectors of dimension m, the m can be very large. For example, in case of images. In that case, it is of interest that if we compress xi to some lesser dimension m1, but still retain most of the relevant information that we need for our machine learning purposes. This can be done as follows. We find dimension w, vector w of dimension m1 cross m, matrix u of dimension m cross m1, such that zi is equal to wxi is a vector of dimension m1. This is the compressed vector, but we want that zi in such a way that using u, if we recover u wxi, this is of dimension m again, difference between this and xi, mod of that square, summed over all I, is minimized. In a sense, what we are doing is from xi of dimension m, we are making vectors zi of dimension m1 so that the original vectors can be recovered to the extent possible. What is the purpose of dimension reduction? This leads to data compression. Data of dimension m has been compressed into data of dimension m1. This can result into, if we work with in machine learning using zi instead of xi, the computational cost can be reduced. If ml is much smaller, then cost reduction can be very large. Storing zi will require a lot less storage than storing xi's. If you want to communicate this data somewhere, so instead of then communicating xi, if we communicate zi, the communication cost will be much less. And also, working with zi instead of xi can enhance the explainability in machine learning, which is becoming increasingly popular. So there are many, many advantages of reduced data processing, and we study this problem further now. This has a very nice closed form solution. It is obtained as follows. Define matrix A as 1 by n summation over I xi transpose. For this matrix A, we get eigenvalues because this is m-dimensional. There will be m eigenvalues, and we put them in decreasing order. Lambda 1 greater than equal to lambda 2 greater than equal to this. These are all real valued, and these are non-negative. So even lambda m is greater than equal to 0. Corresponding eigenvectors we denote by u1, u2, um. Then we take u, the matrix that we have, u and w, that we are defining now, given in the last slide. U is this matrix given by column vectors u1, u2, um1. Each one of the column vectors is dimension m, but the number of columns right now is m1. W is defined as the transpose of this, and therefore has dimension m1 cross m. And this way, the U and W that we obtain will provide the optimal compression as we have just defined. Often before we do that, we centralize the data. This is done as follows. We take the sample mean of the xi observations, then from xi we reduce mu and create new xi's. And A is generated from this new xi's instead of the original xi. This method, and then of course you take eigenvalues and so on. This method is called principal component analysis. And this is a very popular method. Now we create the quantum version of this method. Again, from xi you subtract the mean. Now, in addition to that, we normalize this data also. Each xi is divided by norm of xi. This way, the data that we'll get is having norm 1. Often in the traditional methods also, we do normalize, but in the method that we are proceeding with further, we need to do that because we use what is called amplitude coding. So this traditional data, xi, before we can use quantum circuits, need to be converted into a quantum data. And there are many ways to do that. What we are using here is the amplitude encoding method. So in amplitude encoding, take this vector xi. It has m dimensions, so which are denoted by xi1 to xim. And then this xi in the quantum data is represented as this quantum state denoted by xi, and this is given by summation j is equal to 1 to m xij. Remember, these are the components of xi and this vector j. Actually, instead of j is equal to 1 to m, you may want to prove it j is equal to 0 to m minus 1. This gives slightly better improved performance. And this is as valid quantum state because of the normalization that we have done above. From these quantum states, we define a state operator rho, which is 1 by m, I is equal to 1 to n, xi conjugate over. So this is the average taken over all the quantum states. For this operator rho, we calculate the dominant eigenvalues and eigenvectors, and from there, we can compute the T uh, and U matrices that we need to compress the data. Going forward, to use the quantum algorithm from rho, we calculate the operator e raised to minus rho t. This can be done via quantum simulation, and from this we calculate using the quantum phase estimation algorithm that we have done earlier, and at the output we get the state where lambda i's were the eigenvectors, eigenvalues of rho, and lambda I tilde are approximations of these. These approximations have been used here, and ei is the corresponding eigenvector for eigenvalue lambda I. Now, we make measurements. If you make measurements on the second register, then we see lambda I tilde with probability lambda I tilde. So if lambda I tilde is large, we are going to see this corresponding eigenvalue with higher probability. And then what is left in the first register are the corresponding large value eigenvectors corresponding to the large eigenvalues. So this way we can obtain with higher probability the larger eigenvalues and the corresponding eigenvectors which we need. These are the eigenvectors that we need for our PCA. This thing. How do you calculate obtain these eigenvectors with higher eigenvalues? We can do the repeated measurements, and with higher probabilities, we are going to use the eigenvectors corresponding to the higher eigenvalues. From that, we can obtain our compressed data. Next method is k nearest neighbor classifier. This is also a very popular method in classical machine learning. In this method, this is used for classification as the classifier denotes. You have training data x1, y1 to xn, yn, xn, xi are the observations with values in Rm. Yi now take values from 1 to n because this is a classifier, and n is the number of classes. Now you pick k, a positive integer. So you can pick k is equal to 1, 2, 3, 4, and so on. And any new class observation x will be via this method classified as follows. Given this k, For this X, find the K observations X from X1 to Xn, which are nearest to X, and nearest in the sense of their norm from Xi minus X norm is the minimum among all these norms that we get here. And after getting the K nearest Xi's, look at their samples, um, labels Y1 to Yk, and from those K labels, we choose the majority label, and that is how we classify the new observation X via this method. Complexity of classifying one point here is of the order of n into m. N is the number of observations, number of observations in the training sequence, and m is the dimension. Now we look at the quantum version of this. Now in quantum case, instead of looking at to find the k nearest neighbor, instead of calculating the difference of the norm, a norm of the difference, we calculate similarity measure, and similarity between x and x prime is given by inner product of x and x prime, take mod square and divided by their norms. So in this case, what we will do is we will, for a new observation x and for given x1 to xn, we will find the k observations from the training sequence which have the maximum similarity from X. So this will have maximum similarity, which is like taking the minimum distance in the classical case. To do that, so now what we are going to do that, given training sequence and given an X that you want to classify, we calculate for each X the similarity from all the X1 to Xn training sequence data, and then calculate the nearest K. For doing this, calculating this quantity, we prepare the initial state like this: 1 by square root of m, sigma I equal to 0 to m minus 1, I, xi. And so this is last register, then this register, and this is the first register. First register is going to have value 0. So this is how we prepare the initial state. Now we perform swap test on the last two registers, this register as well as this register. After doing the swap test, we measure the first qubit, which initially had 0, and then the output of it will be 0 or 1, and the probability of output being 0 is P0, that is given by this quantity. So once we have taken the measurement of the first qubit, after that, we measure the last qubit with respect to I cross I tensor I. The output of that qubit will have value I, given that the first qubit had output alpha. Alpha could be 0 or 1. So this probability is Pu, output is I, given alpha is given by this quantity. And Qi we define as Pu I given 0 minus Pu I given 1. Pu I given 0 is higher, as you can see from this expression, or this expression if you want to take, is higher if the similarity of xi from this x observation is higher. And once, so that is one thing. And if you calculate Qi, then the corresponding Qi is even higher. And therefore, instead of choosing this, we pick Qi to get the observations xi's which are closest to the new observation x. So pick Qi, which have the nearest, which are the nearest over x, and that's how we can classify this x. Now, to get this Qi, which is obtained this way, we need to have these two probabilities. These probabilities are computed by repeated measurement of the first qubit. Now we talk about the next class of circuits, This is a general class of quantum circuits called quantum variational circuits, and this has been recently found to be very, very useful, especially in the near uh, term context when the qubits are still not very reliable. And so this kind of circuits, quantum circuits, have been found to be very useful. Now we use this concepts for getting quantum machine learning algorithms. Again, we start with the training data x1, y1 to xn, yn. And right now we'll consider the classification problem. But the regression problem can be considered in the same way. Now, given this data, we considered a quantum circuit, and we will explain how we will make a quantum circuit. This will be a circuit with some parameter theta. If this parameter changes, then the circuit changes. So this is parameterized, variational quantum circuit with parameter theta. Given this theta, the main output that we are going to measure, that we will call f theta, and given x, the main output given by f theta x will give us y. We want to find theta. So if it is a classification problem, we want theta, this parameter, that minimizes the error in the training sequence. So what is the error? For a given theta, f theta xi is the classification given by the circuit. And if that is different from the label yi or xi, you would sum over all of them, then that gives the average error for a given quantum circuit theta. We find theta which will minimize this error. Okay, now we explain how these quantum circuits we are going to make. The quantum circuit is going to be denoted by ux theta. Theta is the parameter that we are talking about. X is the input. So the output state that we have been talking about, which we are going to make measurement and take the mean to get f theta, is going to be by taking at the input state 0 and getting the state phi x theta by passing this u through the circuit ux theta that we just mentioned. And after getting this state, you make measurements with respect to operator m, which may have component ml that we are denoting here. Then the mean of the output, which is f theta for a given x, is given by summation over L, this ML given here, this index L, multiplied by PL x theta, where PL x theta is the probability that L will be observed on measurement using these operators. Now we talk about what kind of circuits use x theta we are going to consider. We have the flexibility to consider many of them. One popular choice that is made is if, let's say, x, the input, the observation is scalar, then ux theta will be given by this sx multiplied by w theta. So theta parameter comes here. So this quantum circuit will depend on it's a parameterized circuit. And this is quantum circuit, which will take input x and give a circuit. Then phi x theta, which is the output state by using ux theta over 0, is given by w theta sx 0. Now, if instead of x as a scalar, if x is a vector, x1 to xn, then this can be generalized to, instead of being w theta sx, we can have w1 theta, w2 theta, wn plus 1 theta, corresponding to these n, and s1 x1. So this x has component x1 to xn. So x1 component goes to s1, x2 component goes to x2, and xn component goes to sn. So this is how we are denoting this u theta x in case of vector x. And you feed to this quantum circuit the input 0, and at the output you are going to get this. These Sx that we have denoted here often are given by Sj, xj is exponential minus I xj gj. And gj also that you have to specify, these are going to be the Hermitian operators. If these are Hermitian operators, then this will be the unitary operators that we need. Now, if we want to do binary classification, so after this, we still have to pick M, right? The operator with respect to which will make the measurement. If we are doing binary classification, the output given by this should have two values. So therefore, M can be taken as Z operator. It has eigenvalues plus minus 1. The outputs can also be plus minus 1. And the outputs given by using this operator on this circuit will provide us the classification into two classes. If instead of two, we have four classes, then M can be Z, tensor Z. Then, of course, the output will be 0, 0, 0, 1, 1, 0, 1, 1, denoting the four classes. Further example of this kind of circuits, Sx that we have noted in this example, we are taking as Rxx. So S operator is this poly rotation operator with respect to X. And W theta we are taking as rotation of theta 1, theta 2, theta 3, where rotation theta 1, theta 2, theta 3 is a general rotation with product of Rx, Ry, Rz. So given theta 1, theta 2, theta 3, this product will R1 theta 1 into Ry theta 2 into Rz theta 3. So this is going to denote our W theta in this particular example. If you do this selection, then the average output, which we are doing f theta x for given this theta vector, is cos theta 2, cos x, x is the input, minus sin theta 1, sin theta 2, sin x. For general ux theta, so we can compute in the same way f theta. So then f theta could be in general vector from function from Rn to R. It will be real valued, and it can be written in terms of cos sine functions, just like in this particular example. This kind of method using variational circuits can be very general. For example, if the eigenvalues of Gi, the Gi that we have discussed, where Sx has been given in terms of equals minus I Gi x, if eigenvalues of Gi's are integer valued, then the corresponding f theta x becomes a multivariate Fourier series. And example of Gi with integer eigenvalues is the poly rotations x, y, z that we have already mentioned. If eigenvalues are rich enough, then any function f from Rn to R can be approximated on any finite interval 0 to t. Therefore, this method, variational quantum circuit method, can approximate, given enough resources, any function from Rn to R, and hence are universal approximators. This is a very important property. For example, in the classical machine learning, neural networks are universal approximators, and so are some of the kernel methods and so on. This property is very important for the machine learning because then we can get a good, using these methods, good classifier and regressors because they can approximate any function. Thank you very much. And in the next video, we will continue further on these variational methods. Thank you.